All right. So I'm just going to look at a couple of these application ones then. Is that all right with you guys? Let me see, which one do I want to look at? Okay. I think maybe we'll look at number 3, and then maybe we'll do grab one of the related rates one. And we'll do 2 of those, and then call it good for me, and you guys can pick up where we left off and pick away at some of these other ones. Sound okay? All right. It says the derivative of function f is given by f prime equals this piecewise function, where the first piece is g of x and the second piece is 5e to the negative x over 3 minus 3. It says the graph of the continuous function f prime, that's some bad rendering, shown in the figure above, has x-intercepts at x equals negative 2. And x equals 3 natural log of 5 over 3. That must be this. The graph of g on negative 4 to 4 is a semicircle. What does that mean? Yeah, like a half a circle. So if we're going to draw the graph from negative 4 to 0, there's my semicircle, right? What's the radius of this, or what's the center of this circle going to be? Negative 2, 0, right? And what's the radius of this circle going to be? Has to be 2, right? I don't know if I need any of that, but I'm going to bother, as long as I get that piece of information, I'm going to write that down to start with. So far, so good. And I know that my endpoints are closed because the interval I'm working on is from negative 4 to 0, and that's a closed interval also. Okay. It says for negative 4 to 4, find the value of x at which f has an absolute maximum. Justify your answer. So the first thing I'm going to note is that this is a closed interval. We're asking to find the absolute maximum or minimum over. So to do a closed interval method, I need 2 things. I need to check the endpoints of the function, and I need to look at the critical values. Everybody feel good on that? So the endpoints obviously are negative 4 and 4, so let's go to the critical values. How do I find the critical values? Okay, so I take my derivative, I set it equal to 0. Now we're told these are the x-intercepts, right? Oh, look, this is so dumb. I'm so dumb. Look, right over here. There's my semicircle. There's my radius of 2. Dirt to dirt. Everybody's okay? Should have looked at the picture more closely. All right. What else do I also need to check? Yeah, I have to look where the derivative does not exist, right? There's the graph of my derivative. Well, the graph of f, or the derivative of f double prime would not exist at 0 because it's a corner. But f prime is fine, right? Everybody see that? That looks like it's they're both at 0, 2, right? So semicircle, that should be the point 0, 2. And if I plug 0 in for x here, I have 5 times e to the 0. So 5 times 1 minus 3. So that looks good. Okay. So we see none here. So I need to check then what things. Not f prime, bozo. Oh, Mr. Kulik, it's not your day. You know why it's not your day? Because what you need in order to do this, to finish this, we don't have. I know. That's where I'm at, Lucas. You know, sometimes this is how life goes. This would be a semester 2 problem, because what do you notice we are conspicuously lacking in order to finish this? We don't know anything about f, right? Now, we have enough to see whether, these are going to be local maxes and mins, because we have the derivative, the graph of the derivative. We can do that. But to do the absolute, we also have to check the value of the endpoints against the values of these things to see if either of them are a local max or min. Like this one we don't have to worry about because the derivative goes from positive to positive, right? This one goes from positive to negative, which means that this is a local max. But to see if it's an absolute max, I have to know these values. Or to see which one of these is going to be the absolute minimum, I need to be able to find those two values. We just don't have the tool to do that yet. We would need an integral in order to do this. It's a second semester piece. And Mr. Kulik's starting to get a bad feeling that he forgot to say, when he searched the MyEP for questions, forgot to say topics no later than this, included topics no later than this, because this one and the other one I X'd out were both integration problems, which is making me pretty frustrated right now, because I feel like I just boogered the whole thing. Anyway, so this we cannot do. I know. All right. Let's do this one. This one I know I can do. And we can do. I mean, I could do the other one also. You guys can't. So, not yet anyway. Okay. So here's the graph of our derivative. I feel like like some of this we can't do. I don't know. Let's continue on. We have the closed interval -7 to 7. The graph f prime has a horizontal tangent at -3, +2, and +5. Find all the values from -7 to 7 in which f attains a relative minimum. Okay, so if I want my relative minimum, what do I need to look at? The critical values. What are the critical values going to be? Everybody agree? Since this is the graph of f prime. At -5, do I have a local min, local max, or neither? Max, because we went from positive to negative. At -1, what do we have? Okay, because we go local minimum, because we go from negative to positive. And how about at 5? Neither, because we go from positive to positive. So far, so good? Okay. So there's our answers for A and B. We did them both at the same time. Everybody okay with that? Find all values of x on -7 to 7, in which the second derivative is negative. So my zeros for the second derivative are going to happen where I have these horizontal tangents. If I look at the slope of f prime, what's happening to the slope of f prime here? Negative. And then if I look at the slope of f prime from here to here, we are positive. And then from here to here, negative. And from here to here, positive. Notice that even though I didn't have the graph of f, as long as I have f prime, I can still talk about f double prime pretty easily, right? I just look at the slope of the derivative. Will tell me about the second derivative. So what do I have here? Then I have -7 to -3, or from 2 to 5. And I don't think we have enough information, because we don't have integration, to be able to do an absolute maximum here. Yeah, we just can't do that. Ugh. Or was that one? I wanted to do this one. I love this one. I think this is the same one that's in the test I just gave you. Is that right, Kate? Yeah. As shown in the figure above, water is draining from a conical tank with a height of 12 feet and a diameter of 8 feet into a cylindrical tank that has a base with area 400 square feet. Or sorry, 400 pi square feet. The depth h in feet of the water in the conical tank is changing at a rate of h minus 12 feet per minute. So I'm going to call this HW con. And I'm going to call this like RW con, because I'm also going to have like an HW cylinder and like an RW cylinder. Everybody okay with the notation? I need to be a little bit careful about my R's and H's here because I have two figures with radiuses and H's. And then I also have the dimensions of those figures. So we're going to say the depth in feet of water in the conical tank is changing at a rate. So this is talking about DHW conical. dt is equal to h minus 12. And it gives us the volume for the cone. Okay. Write an expression for the volume of water in the conical tank as a function of h. This first question is not a calculus question. Rather, it's like a geometry question. So there's my volume of a cone. It's got an h in it, right? What we need to do is we need to get rid of the r squared in it. So we just need to eliminate the variable of r. If your figure is a cone, what trick did we use to do this? Because we've done other related rates problems involving cones before, right? Where we've had to eliminate a variable. What do we have? Similar triangles, right? Whoa. You okay? Okay. So the height of my cylinder is 12, that's given to me, and the radius of that cylinder is 4, that's given to me. So I can say like height of cylinder over radius cylinder is equal to the height of the water in the cylinder over, not cylinder, gosh dang it. Like I'm happy that you know, like in a way it's really convenient that we picked cones and cylinders for this, but like the C thing is like cones, it just drives it, like I'm gonna make this mistake the entire time. So this is the guy we want to isolate, right? The radius of the water in the cone. So I can multiply both sides by 1 over HW cone and then flip. Everybody's okay with that? Or you cross multiply and then divide, whatever. I'm not going to show the algebra if that's okay with you guys. So in this, we really have 4h over 12. I did it over here too, didn't I? I called these things cylinders. God bless it. Or really just h over 3. Feel okay? So my answer for part A, then, I take these two together. Do that. And do a little combining some like termies, and there we go. Feel good? Okay. Says, at what rate is the volume of water in the conical tank changing when h is equal to 3? Indicate units of measure. So we did the hard part here initially. So we have this thing. All I really need to do with this now is to take the derivative of it with respect to time. So when I take the derivative of v, what do I get? I heard some mumbling. I hope the mumbling was dv dt, or 1 times dv dt. That would be fine as well. But we don't really need to write the 1 there. What's the derivative of h cubed pi over 27? You got that guy, right? So far, so good. Might as well do some little reducing there. So what we have is dv dt when h is equal to 3 is going to equal 3 squared pi over r times 3 minus 12. Or negative 9 pi. Feel so far so good? The question also asked us for a unit. Said include units. So what do we here have going on? Depths are in feet. So the volume is going to be in cubic feet. And then the rate is per minute. So this should be cubic feet per minute. Does that feel okay? So responsive today. I love it. Keep it coming. Staring blindly at me like, ugh. C says, let y be the depth in feet of the water in the cylindrical tank. At what rate is y changing when h is equal to 3? So we want dy dt when h is equal to 3. And really this h here, let's be careful. Talking about the h for the cone. far so good? Okay. So, what equation are we going to use here to start with? Let's start with some equation. What shape is y part of? A cylinder, right? So we probably want some equation concerning a cylinder. What equation do you suppose we want about cylinders? I would think volume as well, because what's happening with the cylinder?
The water's
It's filling up with water, right? What is water occupying? Volume. Everybody feel okay with how we reason out that volume is probably the equation we want here? Okay. So the volume formula for a cylinder is just area of the base times the height. But I'm going to be a little bit careful here. And make sure I write these as cylinders to avoid confusing the radius and height for the cones. Is that okay with everybody? Now, in our case, the height of our cylinder is y, right? Everybody agree? Because that's we have this water-shaped cylinder sitting in the container. So, oh my goodness, pi r squared, dingbat. Okay, so before I continue, let's think about r here. Who sees the important observation I can make about r? This is what takes this problem from being something it's impossible to do to be something that's quite easy. Look at the shape. Think about how it's changing. The radius is constant, right? As that cylinder fills, the radius of the circle at top is the same at any height, right? Oh, that helps so much. Who's excited about that? You should be. It's an exciting happening. How are we going to figure out what that radius is, though? It's a number. It's just a number. And it's a constant all the time. How can I find that number? What piece of information haven't we used yet?
area.
Yeah, the area of this base was 400. So this is just equal to pi r squared, because it's the circle. Oh, yeah. So r is 20 then. Everybody feel good? Really, it's plus or minus 20, but like, do we need to say that negative radius doesn't make any kind of lick of sense? Probably not. We can just go straight here. All right. So the volume of the cylinder. And I'm going to put water in here just so that it's clear. And I'm just going to call that Y. Okay. So far, so good. What should we do next? Differentiate? Sounds good to me. So far, so good? Mr. Kulik, for me to solve for dy dt, I gotta know what that is. What's the rate that water's changing for that cylinder? What? 9 pi. That's excellent. How'd you come up with that? Share us. Illuminate. So if 9 pi cubic feet of water per minute is coming out of the cone at that instant, that means that 9 pi cubic feet of water is coming into the cylinder. That's why the sign had changed from negative to positive, because in the cone the water is draining out, the cylinder it's filling up. Really important observation there. Nice job. That's not, I mean, it's obvious when you think about it, but like, this is why, like, really understanding what's going on and looking at the structure makes these problems hard, right? Because we just did we did math stuff for not math reasons. We had to actually, like, look at the situation and think about in the real world what is going on. And we did math things for real world reasons, which is kind of hard to catch sometimes if you're not looking for it. But yes, that'll do us. So we have dy dt when h is equal to 3 is going to be just 9 over 400. I canceled the pi's when I did the division. And this would be, the unit would be feet per minute because it's just a length. So I liked this particular related rates problem. As you can see, it made it onto the test and it made it onto the sheet. Really because, one, I like that they kind of stepped you through. It's like here, if you can't do part A, like where you can get the equation in terms of a single variable, like there's no sense in trying to ask you any of these other questions. Like you have to be able to do that first. So it kind of cues you to like, hey, eliminate a variable for this without having to like, you know, without leaving that for something for you to notice on your own. It's like telling you you must do this. And then I really liked part C a lot because you're so rewarded for like understanding the situation. Like if you don't catch that R is a constant, you're sitting there stuck going, okay, I have to do a product rule when I differentiate that. I don't have dr dt. How the heck am I going to come up with this? Do I need to eliminate a variable? And it's like, well, I really shouldn't have one variable to start with. You just didn't notice it, you know? And then the dv dt observation that Anthony made, again, like recognizing that, oh, the answer for my previous part is the piece that I'm missing here, that the volume coming out of this thing has to be the same as the volume going into this thing, and then having to do the sign flip, right? Like, this is a nice problem. Nice problem. What do you guys think? You feel adequately warmed up here to tackle some on your own? I'm gonna stop talking. I'm gonna let you guys tackle some stuff. I'm gonna do these problems alongside, and if I run into another thing that you can't do yet, I'm gonna let you know. Sorry that you're my guinea pigs. Ideally, I would have done this in advance, but like, I've been buried under IBSL, like, nonsense for the last, feels like the entire week here. So, and I'm gonna get buried again some more on Monday, and just, it's right now, so, and not as caught up as I'd like to be. Is that okay? You guys good? Okay. If you have questions or stuff, like, feel free to come up and talk to me. Feel free to work together, you know, like, share your knowledge.